Welcome to Study Loop.
Okay, we're looking at question 28.36, and we have a circular coil with radius 2.4 centimeters, and we're looking for the current in the wire if the magnetic field at the center of the coil is 0.077 Tesla. So we're trying to solve here for the current. So to use this, we're going to need to use this formula for the magnetic field along the axis of a circular loop of wire. So we have on the top U naught times N, the number of turns, times the current, and A is the radius here. And I've listed the quantities that we have over here and converted them to SI units. I've converted the 2.4 centimeters to meters, so we have that readily available to us. And then that's divided by 2 times x, where x is the distance from the center along the axis of the coil. And then a again is the radius, and that's raised to the power of 3/2. So when we're first looking in part A here, we're looking at the center of the coil. So at the center of the coil, x is equal to 0. So we can get rid of that term when we actually start plugging things in here. So when we look at this, we're going to end up with a factor of mu naught up at the top when we start plugging this in, times n times I, and then we have our a squared. Now let's look at the bottom here with x equal to 0. When x is equal to 0, we have 2 times then this factor of a squared raised to the power of 3/2. And what that does, a squared to the 3/2 is going to simplify to just a cubed. If we take a look at this, we have a squared on top and a cubed on the bottom. And that's going to cancel out to just a simple factor of a in the denominator. So we can write this easily as this. And this, I'm going to just label this BC because this indicates the magnetic field at the center of this coil. So technically what we're given here is BC, the magnetic field at the center. So now all we have to do is rearrange this to solve for I, because I is what we want. So we're going to end up with 2 times A times BC here when we multiply both sides by BC. That's going to be equal to our mu naught times N times I. And then to solve for I, we're going to just divide both sides by this factor mu naught times N. So we get over here mu naught times N, and this is our I. I'll just write this on the other side. So this is what we want to solve for. Now we just have to plug in A is 0.024, BC 0.077, our factor of mu naught, and N is 800. So when we plug that all in, we get I is equal to 3.68 amperes. So that's the answer to part A. Now for part B, we're asked at what distance x from the center of the coil on the axis of the coil, so this is our x here that's coming in, when is the magnetic field half its value at the center? So, all right, now I'm going to pull this over here. This we figured out from part A. So we want to figure out, basically we're looking for some distance, some magnetic field Bx, where it's BC, the magnetic field at the center, divided by 2. This is what we're trying to solve for. And our Bx is going to be this big expression here. So this is really our generalized Bx, because this is at some distance x along the axis. So we have this big equation up here. Looks pretty complicated, but then take a look at BC. We have this slightly simpler version. So let's see if we can pull out a factor of BC here, because we have the same numerator mu naught and I, and then we have 2 on the bottom, so we can pull that out also. Basically, we're just looking to factor this. And we just need to pull out a factor of A from the numerator, from the denominator. So what that can do is just increase this factor of A squared to an A cubed. So let me just write this out so you can see what this means. we're basically going to write bx is equal to bc, which is this thing over here. And then that pulls out our factor of mu naught n and I, but it's going to leave us with an a cubed in the numerator. So we'll leave this like this. And then our denominator is going to still be this relatively complicated thing up down here. Notice that what this does for us is it makes us, we can now put this into slightly more simple terms. So looking at these two equations, this is what we want to solve. Essentially what this tells us is that this whole term, this part over here, needs to be equal to 1/2. So when we plug this in like this, we get that this term has to equal to 1/2. And if you kind of stare at these equations, see that this bx here, bc here, this divided by 2, this tells us that this whole term needs to be the equivalent of dividing by 2. So this needs to be equal to 1/2. So that's how we get this here. Now, we want to simplify this out a bit, obviously, because what we're trying to do here is solve for x. And we can simplify this by, if we can write out this in terms of x squared plus a squared. We're multiplying both sides by the denominator here to the 3/2. And that's going to be equal to this divided by 2 is going to be equal to a cubed. Now, let's multiply both sides by 2 so that we don't have to keep a fraction on both sides. This is just rearranging this equation up here like this. And now let's square both sides so that we get rid of this annoying fraction. So when we square both sides, we're going to get this raised to the power of 3, and then this becomes the power of 6. So this is kind of about as much as we can really simplify this here. We don't actually need to go through all of these exact steps. We could just start plugging in numbers if we wanted to. But just to save ourselves a little bit of plugging stuff into the calculator, remember, we know here what a is. So all we have to do is plug in for a and then solve for, oh, sorry, this is also going to become, this needs to be squared. So we needed to bring this as a 4. When we squared all the terms on each side, this had to be raised to the power of 2 as well. So we have the value for a here, and essentially all we have to do is just plug in the numbers and solve for x here. So I won't show the exact calculations, but when you plug this in and solve, you should get that x is equal to 0.0184 meters.